Hello and welcome. Today, we're diving into the tiny world of semiconductors and a technology that's making our gadgets smaller, faster, and more powerful. Extreme Ultraviolet Lithography, or EUV. So, what is EUV? Imagine trying to draw incredibly fine lines. You'd need a very sharp pencil, right? In chip manufacturing, lithography is like drawing circuits onto silicon wafers. Traditional methods, called deep ultraviolet or DUV, use light with a wavelength of 193 nanometers. EUV uses light with an extremely short wavelength, just 13.5 nanometers. That's like switching from a regular pencil to an ultrafine tipped pen. This shorter wavelength lets chipmakers etch much smaller patterns, which is crucial for creating the microscopic transistors found in today's 7, 5, and even 3 nanometer chips. Why does this matter? It's all about keeping Moore's law alive, the observation that the number of transistors on a chip roughly doubles every 2 years. EUV is the key technology enabling this continued miniaturization. More transistors packed closely together mean faster processing speeds and lower power consumption. This benefits everything from your smartphone and AI processors to self-driving cars and advanced memory. Major players like TSMC, Samsung, Intel, SK Hynix, and Micron are already using EUV to make their most advanced chips. It can also simplify the manufacturing process compared to older techniques that required multiple complex steps for the same result, potentially improving efficiency. But EUV isn't easy. It comes with significant hurdles. First, the cost. An EUV machine from the sole supplier, ASML, costs over $150 million and uses a massive amount of power. Second, complexity. EUV light is absorbed by almost everything, even air, so the whole process has to happen in a vacuum using complex mirrors instead of lenses. Generating enough powerful EUV light efficiently is also tough. They need high-power sources to process wafers quickly and make it cost-effective. Companies are constantly working to boost this power, currently aiming beyond 250 watts, and researching potentially more efficient laser sources. Then there are the masks, the stencils used to project the circuit patterns. They are reflective and incredibly sensitive to tiny defects. Even microscopic flaws can ruin chips. Developing better mask inspection and defect-free materials is vital. Finally, the light-sensitive chemicals used in the process, called photoresists, need constant improvement to achieve the required detail without sacrificing speed or quality. The quest for smaller doesn't stop there. The industry is already moving to the next generation, high numerical aperture EUV, or High-NA EUV. Think of numerical aperture like the aperture on a camera lens. A higher NA allows for finer detail. High-NA EUV increases the NA from 0.33 to 0.55, enabling features down to 8 nanometers. This is essential for future chip generations below 2 nanometers, like the planned 1.4 nanometer or even 1 nanometer nodes. ASML shipped the first High-NA system in late 2023, and companies like Intel and TSMC plan to use it in production around 2025 to 2027. These machines are even more expensive, estimated around $384 million each, but they promise to simplify the manufacturing steps needed for these incredibly small features. Looking even further, ASML is already talking about Hyper-NA EUV with an even higher NA, potentially pushing below 0.2 nanometers after 2030. For the foreseeable future, EUV and High-NA EUV will be the workhorses for cutting-edge chips powering AI, high-performance computing, and advanced mobile devices. While older DUV technology will still be used for less critical parts of the chip manufacturing process, EUV is indispensable for the most intricate layers. Continued innovation and investment in EUV and its ecosystem are absolutely critical to keep pushing the boundaries of what's possible in our digital world. Thanks for tuning in.